Still continuing on with bonding, now we will do the bonding for polyatomic ions. So far we have done bonding for just the neutral substances, ionic substances, and then neutral covalent compounds. Now we get into polyatomic ions, and since we are talking about ions, we need to talk about formal charge. Okay, ions means that you have some charge left over. Okay, so that charge is what we'll be talking about in this section. All right, so first of all, writing structures for polyatomic ions. Now polyatomic ions can get a little bit complicated. Okay, I've kind of gone over the simple rules for writing a covalent structure, right? That you count all the electrons, then you form single bonds, you subtract electrons, you assign all the other electrons, then you subtract electrons, you then pair up single electrons, all those kind of things I've gone through with you. For polyatomic ions, it's really important you do that, okay? So I have kind of also taught you the shortcut for writing structures, which you can still follow here a little bit, but you can't, not all the time, okay? Because you have ions now, and when you have, any kind of ions, it means you have either less electrons or more electrons. And when you have less or more electrons, in those cases, sometimes the atoms that are supposed to have a certain number of bonds may not have those. So nitrogen, for example, is supposed to have 3 bonds. In an ion, it may have 2 or 4. Okay, so you don't know that, so you really can't take a lot for granted here. Okay, so you have to really write the structure in a very systematic way. Okay, so you have to follow the rules. So you can read these rules here, and then let me show you some examples, because that's really what it matters. Okay, is to show you how to do it, and you have the rules here to follow with if you want to read them. Okay, so let's say over here we're writing the structure for NO3 minus, so that's a nitrate ion. Okay, so the first thing you have to do then is you have to add all the electrons. I'm going to do the electronic bookkeeping with you because I still do that also in some cases. Okay, just to make sure that I have all my electrons and I have all the bonding property. Add all the valence electrons in this. Okay, so nitrogen, we have 1 of nitrogen with 5 electrons, okay, in there. So this is nothing different than what we have done before. Nitrogen is in group 5, so it has 5 valence electrons, and that's it. Oxygen, here we have 3 oxygens, and so each of those have 6 electrons, and that's because it's in group number 6. So 6 times 3, 18 electrons. Okay, and now because we have an anion, and that's a -1 charge, you have to add that electron also, okay, in there. So you add all these electrons up and you come up to, say, 24 electrons. So which means that by the time you're done bonding everything, you should have bonded 24 electrons. Bonding, non-bonding, whatever it is, account for 24 electrons, okay, in your structure. That's how it should be. So the first thing you will do, as usual, is you will keep one of the elements in the middle, and that element is still the one with the highest valency, okay, which is nitrogen over here, because it's on the left-hand side of oxygen. So you put nitrogen in the middle, and then you put the oxygens all around with 1 bond, okay, and then that is 6 electrons. So you subtract 6 electrons from 24, that's 18 electrons left now. Okay, so you've accounted for 6 electrons with these 3 bonds. Now what you can do is you can give 1 bond to oxygen. Why can we do that? This is where our shortcut is going to be applicable. We know that nitrogen can have up to 4 bonds. Why can it have up to 4 bonds? Okay, because we said it can have 3 bonds. First of all, this is an ion, so you're going to have some unusual stuff going on. The other thing is you have to follow the octet rule. So you cannot have more than 8 electrons. So nitrogen with 4 bonds is still following the octet rule. Okay, whether it is following the rule of having 3 bonds or not, that's a different thing. Okay, but at least it's not breaking the octet rule, which is the most important one here. Remember, we have exceptions also, okay? So that's a different thing. But here, nitrogen is not breaking the octet rule. And oxygen here is going to be happy because oxygen, remember, likes to have two bonds. So oxygen here is going to have 2 bonds. You can give that double bond to this one or this oxygen also. It doesn't really matter, okay? That's going to be fine. But only one oxygen will get the double bond, because as soon as you put a double bond on this oxygen, and this oxygen. Now nitrogen is going to have 10 electrons, which is not possible. Okay, so only one oxygen is going to be happy here, and that happiness right here, and you have now 16 electrons left because you've added those 2 electrons for the oxygen nitrogen bond. Okay, so now you have 16 electrons left over. Now, when you have a double bond on oxygen like this, okay, like this one, that means that oxygen is all set, right? Because oxygen is supposed to have 2 bonds. At that point, you can assign the lone pair of electrons on oxygen. Remember how many electrons oxygen has? 6 electrons, okay? 2 are bonded, 4 are left over. So you assign those 4 electrons to the oxygen at that point because you know for sure that those 4 electrons belong on oxygen. So you go ahead and subtract those 4 electrons from 16, which was left over from previous time, and now you have 12 electrons here. So 12 electrons are now left over, okay? And you have only these 2 oxygens. Remember, nitrogen cannot have any more electrons. It's done. It's like I'm full. I got my 8, okay? So oxygen now is the one remaining with electrons. And so now what you do is, since both of them kind of look alike, you're like, okay, fine, I'm just going to distribute those 12 electrons equally on both. So you divide the 12 by 2, and that is 6 electrons each. Okay, so 6 electrons go here and 6 electrons go on this one. I don't know why I flipped it, but I flipped it. Okay, well, so long it's flipped and not a wrong structure, that's all that matters. Anyhow, so here is, the 6 electrons, here are the 6 electrons, and we are all set. Okay, for the nitrate, all the 24 electrons are now accounted for. And if you are not sure that I have the 24 electrons or not, then all you have to do is count. Okay, and how do you count? You go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12. So 12 times 2, that's 24. Okay, so all you have to do is count the number of pairs you have, and then each bond is, of course, the one pair. All right, so that's how you will make sure that you have all your electrons in there. So it's a systematic way of, writing structures, and this is really the best way of writing it. If there was any shortcut, you know me, I will tell you, okay? But there is no other shortcut for this one. The shortcut actually is practice. Okay, that's the shortcut. Okay, so let's write for PCl4, and this is a positive ion, so a cation. Okay, let's see how we do this one. So valence electrons again, so phosphorus is going to be 1 times 5, and that's 5 electrons then. And then chlorine, we have 4 of those, and each one of those has 7 electrons as their valence electrons, so that's 28. Now, you better make sure that you add and multiply properly, okay? Because that's another place where you can go wrong. Sometimes we work too quickly and then we miss electrons, okay? So be careful with that. And then since this is a cation meaning that you lost 1 electron. So you subtract 1 electron, okay? So 28 plus 5 minus 1 gives us 32 electrons. Okay, so which means that we have to account for 32 electrons, which seems very daunting, like, oh my god, I have 32 electrons, but it's not that hard, okay, because the structure is going to be very symmetrical because you have 4 chlorines in there. Okay, so again, put the phosphorus in the middle. Why? Because phosphorus is on the left hand side of chlorine, so put phosphorus in the middle and then add 1 bond to each chlorine there, make it nice and symmetrical. So 4 bonds, subtract 8 electrons, so now you have 24. And so phosphorus can have 5 bonds, okay, that's for sure. Phosphorus is one of those exceptions, okay. It can have 3 bonds, 4 bonds, 5 bonds, it can have that. So, but here what we are going to try and do, because this is an ion, this is not a neutral substance, okay. So to make it symmetrical, what we need to do is just see if we can distribute these 24 electrons on chlorine itself, okay. So we can do that. So 24 divided by 4, that's 6 electrons. So we give chlorine 6 electrons each. Okay, and so then we know that all electrons are accounted for. Now, when you write these structures, okay, and this is one of the points of doing this kind of a mathematical calculation and writing these structures step by step is sometimes, you can be writing a Lewis structure and somebody else could be writing a Lewis structure, and you both may have a different structure, but you may have the same number of electrons. So does it mean one of you is wrong? Well, no, both of you are okay, but one of those structures is going to be more stable than the other. Okay, so for example, if I said, okay, I want to give 5 bonds to phosphorus, the only way I can give 5 bonds to phosphorus is by having a double bond on chlorine, which I cannot have a double bond on chlorine. Okay, because chlorine as a terminal atom should have only one bond. Why? Because chlorine as a terminal atom cannot have more than 8 electrons. Okay, so I have to then account for that. If I were to give a double bond to chlorine, then my chlorine may not have paired electrons. Okay, so you kind of have to see the structures and then decide which one is better. Okay, and we're going to do that also in this chapter right now. Okay, but you kind of have to take it step by step and then decide, okay, this is a better structure than the other. Okay, then here, this one, I don't know why I have this here. Okay, to remove that. So now let's talk a little bit about formal charges, because since we're talking about ions, when you have ions, you have a charge, okay, either plus, minus, whatever it is, there's a charge left over, okay, in there. So how do you calculate that? And also, what the heck is it, So formal charge actually is designated to an atom in the Lewis structure, a very specific atom. So for example, we were doing nitrate before, right? NO3 minus. So where does that minus belong? Does it belong to nitrogen? Does it belong to oxygen? Which oxygen does it belong to? So that's kind of what we do with this calculation of formal charge. Okay, how do we do this? Keep it simple, okay? You do it my way, okay? And my way is the easy way. So formal charge, which for me is going to be a shorthand of, FC, valence electrons, VE, minus the number of bonding electrons. So the number of bonding electrons, this is what you do here, okay, is the number of bonds, because this will be the easy way for you. The number of bonding electrons, if you take that, you will have to divide it by 2. Okay, so don't do that. Okay, it's much better for you if you do the number of bonds. Okay, so how many bonds an atom has, and that should take care of your bonding electrons. And then you subtract the non-bonding electrons, okay, in there. Now when I do examples, you will see how easy that is, okay? So I don't know if it sounds complicated, but it actually is not. So valence electrons minus the number of bonds minus the non-bonding electrons will give you the formal charge, okay, in there. These are my shorthands, okay, that you're going to see, because I try to do this very systematically. So valence electrons, bonding electrons, and then lone electrons, okay? The non-bonding electrons, I don't write NBE, I just like LE, okay? Lone electrons is just easier to handle, okay? And then once you subtract this, you will get a number, or not, or 0, so you get -1 + 1, 0, whatever it is that you get, that is the formal charge. Now usually the formal charge is going to be either +1, -1, or 0. Okay, I have not seen -2 or +2. There can be a total charge of -2. So for example, sulfate, it's a total charge of -2, but itself, each atom is, you'll have to calculate for that, okay, and see if it's going to be -2 or -1. So that's kind of how it goes, okay? Now the formal charge is not really a real charge, okay, in the sense that it's just a charge that is assigned, okay, because it really totally belongs to the entire structure, okay, and this is good for knowing where the electrons are, okay, essentially. So, and that's really what our goal is over here, is just to figure out where the electrons are, okay, because that's what we do in Lewis structures. So here is an example. Okay, so we'll start with water, which is a simple molecule, and I'll show you how I work on this, because the next few slides that I have is really just about calculating formal charges and writing Lewis structures and whatnot. So formal charge is valence electrons minus bonding electrons minus lone electrons. Bonding electrons is the number of bonds. Okay, that's all we're doing here. So here is for water. So you have to write the Lewis structure. And by the way, if your Lewis structure is wrong, formal charge will be wrong. Okay, so your Lewis structure really should be good. Okay, should be correct for all of this things that we do. So here is the Lewis structure for water. Okay, so here we'll calculate for hydrogen and then oxygen. So valence electrons on hydrogen is 1. Valence electrons on oxygen is 6. Bonding electrons on hydrogen is 1. Bonding electrons is technically 2, okay, because one is from oxygen, one is from hydrogen, but the number of bonds is 1, okay. So if you want, you can write your structure like this. So then you can say, oh, okay, only have one bond, okay, in there. So hydrogen has only one bond, and that's you subtract that 1. Okay, from there. Lone electrons, no, there is no lone electrons left here. Okay, oxygen does have. So oxygen then, 6 electrons, that's the valence electrons from the periodic table. Bonding electrons, yes, it does have bonding electrons, so which means there has 2 bonds over here. So that's the 2 bonds, so you subtract 2. And then the lone electrons, there are these 4 lone electrons. So you subtract those and then you get 0 and 0. Okay, for hydrogen there is 0 and for oxygen also there is 0. 6 minus 2 minus 4 is 0, which means that there is no formal charge, okay, on this. You might say, oh, I could have told you that, you know, looking at water, I'm like, there's no charge on there. But sometimes what happens is that molecules can be neutral, but they can still have a charge, okay, which means that sometimes internally they can have a -1 and a +1, and when they have that, then you know the total charge on the molecule is still 0, okay, but there is still a formal charge. And those kind of molecules like would be unstable, okay, a little bit, because formal charges are actually not good, I would say, but they lead to instability, okay, in there. So that's kind of what happens, and that's why we calculate formal charges, okay. So here I've written that for you. Stable compounds generally have no formal charges, okay, technically speaking, whether totally or internally, there should be no formal charge, okay. That's what makes a compound more stable. So the polyatomic ions that we have, the addition of all the formal charges will result in a charge on the polyatomic ions. So nitrate, NO3 minus, has only -1 as a charge. So there could be more charges in there, but by the time you finish adding them, they should all result in -1. Okay, so that's kind of what it is. And then when you're trying to figure out which structure is more stable, the fewer atoms that have formal charges, the more stable that structure will be. So as I was saying, that you know, if you and your friend, you're working together and you know you have different structures, the best way to resolve which structure is good is to calculate the formal charge, okay, and see which one comes up with fewer formal charges on there, and that's the winner. Okay, so here are some more calculations. Okay, so N2O and H2SO4. So I've given the Lewis structures also. Hopefully you can see the Lewis structure and see how they are drawn, okay, in there. And then that should give you a little practice also, okay, into what these structures look like. So here is N2O, okay. N2O is a real weird structure, okay. So I mean, I probably will not give you that. That would be like a challenge, okay. Because who would have thought that, you know, nitrogen would be a single bond and nitrogen here would be triple bond here. So it's kind of looks very unstable, you know, and that's the point. Anyway, so here is N2O, okay. So what I've done is I've written the atoms underneath it, and then we're going to calculate all the charges. So again, valence minus bonds minus lone electrons, okay, that are on there. So nitrogen 5 and 5, right? Oxygen has 6 valence electrons. I'll take it atom by atom. How's that? Let's do that. So the first nitrogen, 5 electrons, the bonds 3, and then the lone pair of electrons in there. So the lone electrons is 2. So 5 minus 3 minus 2 gives us 0. Now the middle nitrogen, still 5 valence electrons, that has not changed. How many bonds does it have? It has 4 bonds. So you write -4. Does it have any electrons left over? No, it does not. So which means that the formal charge is +1, okay, on nitrogen. Then for oxygen, oxygen is 6 valence electrons. It has only one bond, so -1, and then it has 6 electrons left over, so that is -6. That's the non-bonding electrons. So 6 minus 1 minus 6 gives us -1. And then you add all the charges up together, 0 plus 1 minus 1, so that gives us 0 formal charge. So which means that N2O technically is a neutral compound, even though internally it has a charge. Okay, now you and your friend, again, you might come up with different structures. Okay, maybe you think, okay, maybe this is the structure. Okay, maybe that's what you think, and that's fine. That's okay. Go ahead, write the formal charges. Okay, calculate the formal charges and see what happens. And if you get fewer formal charges for this structure, then maybe this is the right structure. Okay, email me. Okay, let me know. Okay, if you get fewer formal charges for that structure, because that's another one possible. Okay, for N2O. Okay, so then let's look at the next one, which is sulfuric acid. Okay, in here in sulfuric acid is we have hydrogen, we have oxygen, which is the two single bonds, and then we have the oxygen with a double bond, and then we have sulfur. So I've just picked out all the different looking atoms because there are two oxygens with double bonds and two oxygens that have two single bonds, and then the two hydrogens are alike. Okay, so we have 1, 2, 3, 4 atoms, okay, that we are looking at. So again, you go through it systematically, right? Hydrogen has one valence electron, it has one bond, no electrons left over, 0. Oxygen, 6 valence electrons, and oxygen, this one here, which has two single bonds. So two single bonds, 4 electrons left over, and so 6 minus 2 minus 4, 0, and go on, and then you figure out that there is no charge left over. I don't know why I have -1 here. It should technically be 0 because yeah, everything is 0. Okay, so that should be 0 there, but anyhow. Okay, so this is for sulfuric acid, H2SO4. Okay. Here is for polyatomic ions now. So here's for nitrate, which we've written the structure before, so we know this is the structure. And then here is hydrogen carbonate. Okay, hydrogen carbonate structure. And for hydrogen carbonate, yeah, that looks fine. So we have 3 oxygens, 1 hydrogen, 1 carbon. Just making sure. Okay, all right, so nitrate, okay, we have 2 different kinds of oxygen. So oxygen with single bond, oxygen with double bond, and then nitrogen. So here is this oxygen, nitrogen, and then oxygen. These 2 oxygens are the same. Oxygen, 6 valence electrons, 1 bond, 6 electrons, 6 minus 1 minus 6 minus 1. Nitrogen, supposed to have 5 valence electrons. It has 4 bonds, so that's -4, and then no electrons left over, so that's 0, so that's a +1 charge. And this oxygen here, it's 6 minus 2 minus 4, so -2 and then -4, 0. Okay, so what do we have now? We have 2 formal charges. Remember this oxygen that we calculated? It's actually 2. Okay, so we have 2 oxygens that are -1 each, and then we have nitrogen, which is the +1, so we have a total charge left over for -1. Okay, that's how it works. So I'm going to let you go ahead and do this one yourself. I don't have to do everything. Now here, just want to tell you this oxygen is different than this oxygen because this oxygen has 1 bond, this oxygen has 2 single bonds, and then this oxygen has double bond. So all these oxygens are different, okay? And then you have the hydrogen. So hopefully I've gone through the table enough for you to understand how the table is working and how you're going to count the electrons, okay? So do this one yourself and let me know, okay, if you have any issues with it. Okay, so here is for stability. So as I said, for stability, because you can determine the stability of any compound by looking at the formal charge, okay? So any Lewis structure with no formal charge is a good structure. That is how it should be, okay? Small number of formal charges are okay, big ones and not so good, okay? So if you're trying to draw 2 structures or if you happen to draw two structures for the same compound, just make sure that the one with the lower formal charges is the one that you think is the correct one. Okay, that's how it should be. Then the negative formal charge generally should be on the more electronegative element. Okay, so remember, electronegativity increases as you go to the right. So it will be preferred to have a negative charge on oxygen than carbon. Okay, so that's kind of what we're talking about here. So here again, this is the structures for H2CO. So I wrote two structures here for H2CO. So here is H2 and then CO in the middle, and then H2 with the carbon in the middle and the double bonded oxygen hanging out. Here the oxygen is in the middle. Okay, so here oxygen has 3 bonds, which you're probably already gasping and thinking, oh my lord, oxygen 3 bonds. Well, oxygen can have 3 bonds. Okay, so here's 3 bonds, and then here's 2. So when you count all these electrons out, it turns out that this one, the first structure, has formal charges, but this structure does not have formal charges, okay, in there. So it's kind of gives you an idea of how this kind of a structure determination works, okay, with stability. Okay, so here is another one, and this one deals with another thing called no, this is not resonance. Okay, I'm not going to go there. All right, so this is just two different structures of the same atoms. So CNO versus NCO. Okay, so which structure is more likely to exist? So it's, again, writing two structures for a set of atoms, which structure is more likely, okay, to occur. So by the time you calculate all the formal charges, and please do that, okay. So for this carbon, for example, it comes out to be -2, which is like, oh my God, -2, because we said that, -2 is very rare. And so right there, very rare, it's happening, okay. And then nitrogen here is +1. So yeah, this doesn't look very happy right now. Okay, on the other hand, if you look at this structure here, then you only have one oxygen with the negative charge on it. Okay, and so this structure looks a little bit more probable than the first one. Okay, so you can determine stability like that also. Okay, all right, going on. Formal charge is the easy way. Of course, there has to be an easy way, okay, to do this instead of writing those tables every time. Those tables are very good though, okay, they are absolute, okay, they will never fail you unless your Lewis structure is wrong, okay. All right, so you know that when I was talking to you about bonding, I said to you that certain elements are supposed to have certain number of bonds. So like oxygen is supposed to have 2 bonds, nitrogen is supposed to have 3 bonds. That's what makes them happy. And what is happy? Happy is octet, okay? So that's the number of bonds they're supposed to have, because that is what gives them the octet number of electrons, which means that anytime they do not have that number of bonds is when they're going to have formal charges. Okay, that's the shortcut. So again, your Lewis structure has to be correct. If your Lewis structure is wrong, then I can't do anything with that, okay, because that's the big thing, okay, with anything that we're going to do in this chapter and also in the next one, okay. So be good with your Lewis structures. So here is your shortcut. Elements that have one more bond, okay, than the octet will have a +1 formal charge. So oxygen with 3 bonds will be +1. Nitrogen, which has 3 bonds, if it has 4, it will be +1. Okay, you can go back into the slides and you can check that, and you can check here also. So any element that has one less bond is going to have a -1 formal charge. Oxygen with 1 bond will be -1, and we've been doing that, okay. So you can do this in a little bit of a faster way instead of counting all the electrons every time. If your Lewis structure is correct, then all you need to do is see how many bonds something has, okay, in there, and then that's it. You're done. You don't have to calculate the formal charge, okay. So for example, let's look at these structures, okay, that I drew for you before also, okay, using the shortcut now. So here is carbon, okay. Carbon has only 2 bonds over here. Okay, so what did I say? If it has less bonds, it will have a -1 charge. But it has 2 less bonds, so it means it is -2. Okay, nitrogen has 4 bonds here. Nitrogen is supposed to have 3 bonds, so which means it has 1 extra bond, so that's a +1. Think of an extra bond as it has given away 1 more electron. Okay, so if it's given away 1 electron, that's a positive, right? Cations give electrons. Anions accept electrons. Okay, so I'm not saying that carbon has accepted electrons. It just hasn't given it. Okay, that's all. So it has the extra 2 electrons on it. Okay. Oxygen here, it has the requisite number of bonds. So that's 0 formal charge. That's it. Look at the structure here. Nitrogen, 3 bonds, 0 formal charge. Carbon, 4 bonds, 0 formal charge. Oxygen, 1 bond, it's supposed to have 2. So if it has 1 less, it means it's hoarding that 1 extra electron, -1. Okay, so this is the shortcut. Okay, again, your Lewis structure has to be correct. Or if I give you the Lewis structure, that's even better, right? So if I give you a structure, then you don't have to do counting all the time. You know, you just have to remember these rules. The last thing for us to do here, just 2 small concepts, the bond strength and bond length. Okay, so just to kind of put, the I on the dot kind of a thing. Bond strength and bond length. Bond strength is, of course, how much energy it takes to break a bond. Okay, so again, the greater the overlap, the stronger the bond. All right, a greater overlap is for triple bond. All right, and you can imagine that because you're sharing so many electrons. If you share so much, then you have a greater strength. Okay, a single bond, not so strong. Okay, so triple bonds are going to be stronger. And the same thing happens with the bond length. The more you share, the shorter it will be, okay, because the electrons get closer together. All right, so here are the numbers for you so you can see how it works also. So here is a triple bond, very strong bond, very high energy to break it, and also the shortest bond. Okay, so if I just give you a few bonds to look, you don't have to give me numbers, obviously. I'm just going to ask you which one is stronger, which one is shorter, and you can do that. Okay, it's a very simple thing. So triple bonds are the shortest and also the strongest bonds, okay, of all. So it's a nice trend. And that's it. Okay, that's how it works.